we dive in, as always, want to start with a quick land acknowledgement. For UW Tacoma, we are based on the ancestral land of the Coast Salish people, and in particular, the Puyallup tribe of Indians. As we're thinking about today's topic, looking at being able to have data on water temperature, that obviously has really significant implications to salmon and by extension tribal treaty rights. And so being grounded in that for the conversation is important to recall. George will talk about this a little bit in his presentation as well, but a lot of his work has also been in collaboration with the Columbia Intertribal Fish Commission. And as you may or may not know, that includes the Nez Perce tribe, the Confederated Tribes of the Warm Springs Reservation of Oregon, Umatilla Indian Reservation, as well as the Confederated Tribes and bands of the Yakima Nation. So just want to call out their contributions, collaboration in this research specifically as we talk about that today. But with that, we're going to get into the nitty gritty research of this, and I'm going to hand things over to George.
Thank you very much, Mariel, for the quick intro, and thank you everybody for making it to today's presentation. I feel really honored. I wasn't really expecting this number of people, so I feel really honored to be addressing so many people interested or around the area interested in my research. So today I'm going to talk about THORR, mapping river temperature from space. And with THORR, I do not mean the superhero, the Marvel superhero THORR. It's a tool which I'm going to talk about in the coming slides. And the main work I'll be discussing is exploring the relationship between reservoir operations and riverine ecosystems, but then with a focus on temperatures or how to obtain water temperature data. Before I proceed into the details of my slide, I would like to acknowledge my research group that I work with here at the University of Washington. The name of my research group is called SASWI Research Group, and it includes these amazing guys that I've been working with, and Professor Faisal Hussein, who is my advisor and in the Civil and Environmental Engineering Department here at University of Washington, Seattle. This work wouldn't have been possible without the immense support from the department, the Civil and Environmental Engineering Department here, and funding made available through NASA Earth Science Applied Sciences. And as Mariel mentioned, very consistent collaboration with the Columbia River Intertribal Fish Commission. So in today's presentation, I'll start with an introduction where I'll just talk about more like the motivation behind the research that I'm going to present, the reason why we decided to develop a tool like THORR. And after the introduction, I'll move on to talk a little bit more about the tool itself, go into how we developed it, what it entails, what it can provide, and then where we've applied the tool that I'll be discussing, as well as where we hope to, or some future applications that we want to use the tool for. And then I'll finish off with some summary and conclusion, and then open it up for questions. So let's move straight forward to the introduction. Here on Earth, in every watershed, we make use of fresh water stored in rivers in diverse ways. We can either harness the river water for either domestic purposes, for industrial purposes, or even as a source of water for irrigation for our agricultural lands. And to harness the water that falls here on Earth, we can construct dams that gives us some level of control to be able to back up the water and to create reservoirs where we can tap the water from the reservoirs for whichever purpose that we are going to use it for. Dams can also be constructed, apart from harnessing the water, it can also be helpful or beneficial in terms of flood control, for power generation, which I think here in the Pacific Northwest, we generate a lot of clean hydropower, which I really like about the area, and for recreation. Yeah, so there are many benefits that we can obtain from just constructing dams. But despite, because of these benefits, we see that because of these benefits, dams are widespread all over the globe. If you take in almost every major river around the world, it has some sort of control in the form of a dam. And as you can see in the panel up there, the blue dots represents dams that have already been constructed. And since the beginning, dams have, I mean, we've seen a peak in the construction of dams around the globe. Um, and with that, because of the benefits, once again, there are still some dams that are earmarked for construction in the near future. And you can see that a lot of them are focused in developing areas such as the Southern America and then West Africa area. So dams are going to continue to be around with us because of the benefits that we reap from them. Despite these benefits that we get from dams, there are several negative impacts or disruptions that are caused by dams, ecological disruptions caused by dams. And the ecological consequences of dams come in several ways. The first one that I'd like to talk about is the physical fragmentation of river bodies by blocking the pathway for organisms that live within the river. So if you take a look at this figure here, before the construction of the dam, fishes could move up and down or to and fro along the river network. But then when there is a construction of a dam, there is that physical barrier that segments the river. They can't have that smooth passage. And apart from the fishes moving through the river, it also holds back sediments, as you can see over here. And then the sediment supply for our beaches is reduced, and therefore our beaches wouldn't be as nice as they are supposed to be, you know. Um, Apart from the aquatic habitats, there are other ecological consequences of dam that is in terms of um, the discharge or the amount of water that flows through the river. Like I mentioned earlier, one of the benefits of dams is for either flood control, or we just back it up for sort of use, and this reduces the peak discharge. So therefore, the pattern of flow through the river is going to change after the construction of the dam. This graph that I'm showing here, give me a second. Yeah, this graph that I'm showing here is um, discharge pattern or the flow pattern in the Mackenzie River before and after the construction of the Kura Dam and the Blue River Dam. And you can see that the peaks used to be higher, and then after the construction, the peaks reduced. Similarly, in a flood control dam along the Green River in Kentucky, we can see that the deep black line, the thick black lines are the pre-dam flow or the natural river flow, but then the gray lines represent the flow, the discharge after the dam, right? And you can see that the peaks are in the natural flow are more variable, but then in the controlled flow, the discharges are just, I mean, less variable, just a very steady discharge out of the dam. And apart from the variability, we can see that there is an extended high flow. If you take a look at this place for this section of the time series, there's an extended high flow. Meanwhile, under normal circumstances, you would expect a relatively lower flow. So this is one of the negative impacts or one of the consequences of dams along rivers. And this particular illustration signifies or it focuses on the quantity aspect, the quantity of water flowing through the river, not just the quantity. Dams also affect the water quality, and by water quality, I'm referring to just the temperature aspect of water quality for now. Um, when we back up water to create the reservoirs, because of the large volume or the large depth the depth of the reservoirs, there is something called thermal stratification, where hot water stays on top when the ambient heat from the sun or solar heat reaches the reservoir, and then cold water stays at the bottom. So in a normal summer period where you expect the water to be relatively warmer, because we would be discharging from the bottom of the dam. The discharge that will be coming out will be slightly cooler than expected, right? And in the colder seasons, the pattern over here sort of flips, where you have relatively warmer water at the bottom and then colder water at the top. And so you see that the regulated flow during the colder months, when the water is expected to be cold, the discharge coming from the dam is warmer. So warmer in the colder or cooler seasons, and then slightly cooler in the warmer seasons. And so, based on all that I've talked about some of the positive benefits that we reap from dams, which is undoubtedly very good. And I've also talked about some of the consequences of dams to the ecology or riverine ecosystem. And we can see that reservoir operations have a direct impact on riverine ecosystems. So in order to manage our reservoirs or operate our reservoirs to yield, the best riverine ecosystem outcome, we need to consider both of the consequences that I talked about, that is the discharge in terms of quantity and then water temperature in terms of quality. And I picked water temperature because water temperature is one of the quality parameters that is connected to many other things like dissolved oxygen also varies with respect to water temperature variation. And there are many other water quality parameters. So temperature is like the chief quality parameter that I'm considering here. But in order to consider both, we've done a good job by considering the discharge or the quantity aspect because of several reasons. Number one, is very easy to assess. You can put it's very easy to install gauges, and then I think over here in the United States there are several gauges that observe some sort of quantity parameter, be it water depth or stage, or the flow itself going through discharge from the dam. But then less attention is given to water temperature because because it's relatively more difficult to assess or measure. But if you take water temperature, there are other means that we can measure water temperature instead of just um, measuring them in situ. And these means that I'm referring to are satellite-based methods. So there are there's a constellation of satellites out there that takes or that observes the Earth consistently or periodically, and we can harness the data that we are getting from these satellites to assess the water temperature, that is the water quality aspect. And in when we are able to harness that data and then assess water temperature, then the bias reduces. It's no longer just discharge or water quantity considerations for reservoir operations, but then we are bringing water temperature considerations into our reservoir operations. And that is what we need to do instead of just considering the discharge, trying to meet the environmental flow or trying to make sure that the discharges are match what the environmental flow requirements would be. We also need to consider if the discharge and then the water temperature that we are also discharging is also meeting the environmental considerations. So, based on all that I've talked about, the question that I asked myself or we asked ourselves in the research is that how can we integrate water temperature considerations into reservoir operations to achieve better outcomes for riverine ecosystems? Now, to help us answer this question, that was the or let me say the question was the motivation for the THORR, the tool that I'm going to discuss here, which is THORR. And THORR, as I said, is not the Marvel superhero, but then it stands for Thermal History of Regulated Rivers. And I'm going to talk more about that in the subsequent slides. So, the traditional method for measuring water temperature is to install measuring probes or gauges along the river. So if you want to observe the water temperature upstream of a dam and downstream of the dam, let's say you just want to study and see how the dam is affecting the river, you can place a water temperature measuring probe upstream of the dam and then another one downstream of the dam. But then this will give you just a point-based measurement. That's measurement at just one location. But we know that rivers or water in rivers, they are constantly flowing. So just measuring at one point may not be as beneficial if you want to do an extensive study. And to obtain an extended assessment of water temperature, one of the options could be to install these point-based gauges, several of them along the river network, so that we can know at every discrete location what the temperature is, and that would give us a very good spatial overview. But this is outright not feasible because it would be very expensive to install all these gauges along the rivers and maintain them, and yeah, it's outright not feasible. And because it is point based, it will be limited in terms of spatial coverage. You can't install in locations that are remote and inaccessible. All right, you have to install in a place that you can frequently access and maintain and do all those things. So you'll be limited spatially. Um, so that leads to the remote an alternate approach to assessing water temperature in rivers, and that is using remote sensing. And what I mean by remote sensing is basically um, using data from satellites to observe or um, um, to to estimate water temperature, and then use those estimates to give a spatial overview of the water temperature. So these satellites can observe the temperature from space, right? And if the water body is large enough, which is usually the case of many reservoirs, it can make that observation. But then one thing we should notice is that, like I mentioned earlier, there's a huge constellation of satellites, several different satellites that have been there or have been in operation since the 1970s. And if you take the Landsat mission, which is launched by NASA, it's been in operation since 1972. But then the satellite that they launched in 1982 has the sensor that is able to sense water temperature from space, right? And because it covers the entire globe, or it covers a wider spatial region, now we are moving beyond that spatial limitation of in situ probes to a wider spatial coverage. So satellite remote sensing gives us that advantage of a wider spatial coverage. And like I mentioned, these satellites have been in operation or have been in existence for since the 1970s. So we have a long-term historical data that we can tap to assess what the river, the 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 temperature of the river has been in times past and how that relates to reservoir operations. If you take in situ probes, the ones that the point-based ones that we have to install, you can only get data as far back as the time that it was installed. So if now we are getting the realization that we need to study water temperature, but then we didn't have any probe installed 2 months ago, there is nothing that we can um, do about that. But then with satellite remote sensing, because the satellites have been in operation for over decades, we have decadal data that we can harness to assess, okay, in the past, how have we been operating our reservoirs and how has it been affecting um, water temperature? I talk about satellites in such a positive way, but then it also comes with certain limitations, and I'm going to highlight some of them. The first limitation is that if the water body is very narrow, um, too narrow for the satellite to observe, then that becomes a limitation. If the spatial resolution of the satellite that is observing it is not enough to observe that small water body, I mean, you wouldn't get any um, good observation for that particular section of the river. And then sometimes if the cloud comes in the way, it obscures the view of the satellite, then you're not going to get a good observation. And so despite the advantage that satellites give, it also has some limitations, which are the spatial resolution of the satellite and then the cloud cover. So given these limitations and then the possible advantages, um, the question that I ask myself in the process of developing this tool is that is it possible to reconstruct the hydrothermal history of regulated rivers in the continuum of space and time using satellite remote sensing? So then we are using satellite remote sensing here, but then if clouds can block the view of the satellites, then we wouldn't have it continuously in space. And if on certain days the cloud cover um, creates a gap, then we wouldn't have it continuously in time. There will be gaps in the historical temperature that we are going to obtain from satellites. And that led to the development of the tool that I'm going to discuss. To develop this tool, we sort of focused in on the Columbia River Basin to start with. And the Columbia River Basin, as we can see, it spans about 7 states: Washington, Oregon, Idaho, a little bit of Montana, a little bit of, I mean, in British Columbia. And then there's, I think, a slight part that goes down there into what? I forgot which state that was, but then it spans several states. And this was the study area that we focused on for the Columbia River Basin. For sorry for the development of the tool. So we wanted to see if we can actually use satellite remote sensing to study river temperature along the Columbia River Basin to see if we can get that spatial overview. And then also in terms of time, can we go back in history and regenerate all the water temperature regimes and then see how the water has been varying. Um, One important thing to note about the Columbia River Basin is that the Columbia River, which is the main river, it spans two different countries, that is Canada and the United States. So it makes it a very good example of where we can reap the advantages of satellite remote sensing. Because if you're in the United States, it might be very difficult to access data from Canada. And if you're in Canada, it might be difficult to access data from the United States. But then with satellite remote sensing, we go beyond the boundaries of the country, and then we can see, because if anything goes on in the Canadian region, it definitely will flow and then ripple into the United States region. So it's very helpful to know what is going on in terms of water temperature and how that would flow to affect water temperature in the United States area. And another reason why this is a very good example is that it has several dams. Um, if you take the red dots here signify the dams. So within the Columbia River Basin, there are several major dams along the Columbia and its tributaries. So then definitely we know that there could be some impact of the dams on water temperature. And if you take the temperature gauge station, the institute temperature probes, it's widespread all throughout the Columbia River Basin. So it gives us a very good example where we can see the assess the performance of satellite-based water temperature measurements and then in situ because there'll be a lot of um, data to compare with. But then if you, despite the fact that I said it has a lot of data, if you take an area like this, an area like this stretch over here, there are two dams in the middle, but then this long stretch, there's no water temperature gauge. So if you want to assess how this dam operation is affecting the water temperature downstream or even upstream, there's no gauge to check or to monitor these effects. And that's where we see the importance of satellite-based remote sensing. So to do this, we number one, we wanted to get a spatially continuous water temperature estimate. So to do this, we broke down all the rivers. I mean, the Columbia River and its tributaries. We broke it down into smaller discrete reaches, and every reach was about 10 kilometer, approximately 10 kilometers. And for each reach, we decided to take information that we can get from the reach itself and around the reach. That is the vegetation, the kind of climate in that area, and then see how best that can help us estimate or generate the water temperature for that particular region if we compare that with satellite observations in the past. So based on the data that we collected around the reach, we combined it with data-driven techniques and what I mean is random forest regression, which is a machine learning approach to help us generate water temperature. And these are some of the examples of the water temperature time series that we generated. The red dots are the estimated data, and then the blue lines over here are the institute or the direct gauge measurements that we had. First of all, one thing I would want to point out, if you look at the time series up above in panel A, excuse me, the institute water temperature or the direct temperature measurements, we had some from 1985 up to 1987, and there was a big gap. But then using satellite remote sensing, we were able to generate data that could fill the gap. And the same over here. And we can see that the data that we are generating or the estimates that we are generating match very closely with the in-situ data. So they fall almost in line with all of them. And if you take a test scenario, a reach or a small discrete segment like reach 2 in panel B, the institute temperature measurement was started only in 2020, right? But therefore, if we were to just rely only on the institute temperature measurement, we wouldn't know how reservoir operations might have affected the water temperature in the past. But then using the THORR tool, we're able to reconstruct the past temperature time series. And the same thing to a similar observation here in panel C, where we were able to reconstruct in from about 2007 backwards. And I would like to also highlight test reach 4, which is basically um, a relatively smaller river, but then using our method, we were able to generate water temperature estimates for the river, even though it was relatively thin, narrower than the other rivers. Yeah. So this is just highlighting the examples of the reconstructed water temperature in the area. And it will be very, I'd say it would be the advantages of such a tool would not be realized if we were to just work on this in the lab and then leave it as just a research material for the shelf. We went ahead to develop a tool, um, an online or web-based version of the tool that makes it very accessible to everybody who has access to the internet. So let's say if someone is in BC and wants to know how water temperature is along the Columbia, you can just go and then go to this website and check the water temperature. You can get the time series. You can download long-term averages and deviations and all that. So this is a picture of the tool that we generated as a result of this research, and you can access it at the link over here. I'm pretty sure we will share the webs the slides later after the presentation, so you can access it and then I'll play with it a little bit. But I'll also make time to also just demonstrate how this tool works before I proceed to some of the applications. And then we've also published this work in Earth's Future journal. Yeah, so if you are interested in learning more about how the tool works, I would encourage you to dive deeper and then maybe go through, but then I'll be happy to answer any questions after the presentation. So in view of that, I'll just pause this slide and then just show you an overview of the tool, how it works, and like some of the things you can do with it. Yeah, 1 minute here. Okay, I'm guessing you can all see my screen. And can I get a thumbs up if you can see my screen?
Yes, that looks great.
Great, and thank you very much, Meryl. So here is the THORR tool. You open, and then it shows you a little bit. It shows you a little bit of some sort of guidelines as to how to navigate the tool. Let me hide this part. Good. And then when you enter, the first thing that you are welcomed with is just the spatial overview. And so the questions that we asked in the beginning, how to obtain, yeah, the question that we asked in the beginning, in order to obtain a geospatial, a spatio-temporally continuous overview of water temperature. Now we have a continuous overview of the water temperature, so you can just hover it along any of the discrete reaches in the Columbia River and its tributaries, and it will give you some sort of like an estimate of the water temperature at the top right corner. And yeah, you can hover around, but then if you click on any of them, it's able to give you the long-term time series that I was talking about. And you can, resample it in monthly, bi-weekly, irregularly, different ways that you can do. You can also get long-term averages or deviations and water temperature. And you can also navigate to specific areas that you want to assess or specific rivers. And you also have the option to download maybe averages over a particular period in the form of a GIS. All right. So these are some of the basic functionalities of the tool. And we are still working on, developing and expanding this tool to other areas around the US, other regions around the US, and hopefully, if I mean the research still proceeds, we would want to expand it to several other areas around the globe. Great. I'm going to stop sharing and I'll proceed with I'll continue with the main slides. Slides working?
Yes.
Great. Yeah, good. So I'm going to continue with this. So, one thing that I would want to highlight, which I think Mario mentioned in the beginning, was that um, we've been working closely with the Columbia Intertribal Fish Commission. And I feel left to me alone, I would have probably developed a tool, or we would have probably developed a tool that is totally not useful, right? Because number one, I've never worked with um all my life I've lived inland, not so close to water bodies, not so close to rivers, right? And so I do not know much about river. If you just take me along, I know as much as I've researched about, like I've read in the papers and all that. So working closely with the Columbia Intertribal Fish Commission was very beneficial because they know what the river is, they know what the river is like within the Columbia River. And I remember when we were developing this, I was so happy the first time I generated my first output that, oh, we're able to estimate water temperature. And then I sent it to them. Look at what we did. And then they quickly came back to like, no, we've been fishing here at this particular location and we know that the temperature is not like this. And then that was more like a call for me to sit back and then look at what I'm doing and then make sure that it's actually very useful and realistic, right? So I feel the collaboration with Columbia Intertribal Fish Commission has been very helpful, more like helping me guide whatever I'm doing to a useful tool that can be, I mean, readily accessible and all that. But then without their inputs, I would have probably generated a tool that is journal publication worthy, but then not actually applicable or useful. So this is just, and I'm pretty sure there are a lot of people on the call, a lot of scientists on the call, and I always like to highlight or buttress that whenever we are doing our science, it's very important to consider the inputs of people who are actually using the science or who benefit from the science. Um, so with that said, I would like to move to some of the applications of the THORR tool. So we've um, done a little bit of further research to see where the THORR tool can be applied. And the first one that we considered was, okay, how does water temperature affect the dynamics of fish within the Columbia River Basin? And we know that the Columbia River Basin or the Columbia River is big for salmon migration, that is migrating from the sea or the ocean back to their spawning grounds, or juvenile salmon migrating out into the ocean. So we did a little bit of study um, using our THORR tool to assess the dynamics of fish abundance. And to do this, still staying within the Columbia River Basin, we focused in on a small area. I mean, it's not a small area, it's the longest undisturbed reach of the Columbia River Basin, which is of the Columbia River, which is the Hanford Reach. It is bordered upstream by a dam called Priest Rapids, which I signify by number 5. And then it's connects to, I mean, it's through along the Columbia River Basin. And further downstream of this reach is the McNary Dam, which is number 4 over here. And number 16 over here is Prosa Dam, which is along the Yakima River, and number 12 right here is the Ice Harbor Dam, which is along the Snake River. I mean, the shaded area, even though I call it the Hanford Ridge, the Hanford Ridge is just about 270 river kilometers, 270 kilometers, but then I just for the purposes of this research, I consider all the stretch of the Columbia River, the entire stretch of the Columbia River from Priest Rapids all the way down to McNairy as the Hanford Reach, just for ease of the discussion in this context. Okay. So we try to see where we can apply THORR to assess how the um, water temperature may be affecting um, fish abundance within the Hanford Reach. And I would want to preface whichever results that I will talk about with the fact that I'm not a fish biologist, but then we just wanted to highlight how, from a reservoir operations perspective, we could probably use a tool like THORR could inform us on how best we can um, operate our reservoirs using the inputs of actual fish biologists or the fisheries folks to compare and see how best we can do it. So not that I'm a fish expert here, but then I'm coming from the perspective of in terms of reservoir operation, how best can we apply a tool like THORR? All right. So for this particular research, we came up with a very interesting approach, which is very engineering bias. And I call this the mass balance approach, where I consider, okay, if the river is flowing this way, we know that fish or the adult salmon that will be migrating upstream will be coming from the downstream. So this is river flow. This brown thing is a dam, another dam or another point. And then we are, as, let's assume this is the Hanford Reach. So we are trying to assess the fish abundance within the Hanford Reach. So fish come in, they cross the McNairy Dam, they go into the Hanford Reach, and then they cross upstream again. And what we wanted to do was, if we are, if we have an indication of the fish coming in and fish going out, we want to see how the fish remaining within the Hanford Reach is affected by the river temperature. And then to do that, we use THORR as our source of water temperature data. And this data is, like I mentioned earlier, it's multi-decadal, and we can combine that with um, fish data to tease out some relationships that can tell us how we can best operate our reservoirs for positive outcomes. Um, some of the key findings, we realized that the sorry, I need to also mention some of the things that the formulas that I introduced over here. Um, so we have inputs, that is fish coming in, output fish going, and then if you subtract the the output from the input, you should get an indication of how much fish is remaining within the reach, right? And then we came up with this ratio called the retention ratio, which is basically the percentage of the fish that came in. Um, sorry, the percentage of the fish or remaining within the reach when compared to the fish that came inside. So we wanted to basically see how this retention ratio varies with water temperature. And we realized that if the water temperature exceeds a point like 19 degrees Celsius, which is considered as one of the stressful water temperature levels for the Chinook salmon, which we are considering over here, the retention ratio drops drastically, right? And this was a very interesting detail that we saw that we feel we wouldn't have known if not for that spatial overview of water temperature afforded by THORR. And we also saw that within the Hanford Reach itself, the water temperature was gradually increasing. And you can see this outlier here. This is because the data that we collected, we cut it off at not the entire year. So we have I think this was somewhere in the summer. So we are getting just a little bit of data peeking over there. So try to ignore this for the meantime because it wasn't the full length of data. But then we can see that there's a gradual increase in temperature within the reach. But then as the gradual increase is also occurring, we are seeing a gradual reduction in the retention ratio. And these are things that we feel are only now possible because of a tool like THORR, right? And like I said, I'm not a fish biologist, but then as coming from the perspective of reservoir operations or as an engineer, this could tell us something. Okay, could we operate the water temperature, sorry, the reservoirs so that when as it's getting warmer, we will discharge more from the bottom to cool it and then probably keep the retention ratio at a relatively stable level. These are all insights that are being brought up because of a tool like THORR and could be maybe investigated further. So, how can we use such insights to improve reservoir management for better fish outcomes? We know that in the summer, we can discharge cool water from the bottom. So if we spill more from the top, then we are releasing warm water. And if we spill, and if we release more warm water, it means that we are getting low retention as per this particular plot over here or relation over here. And if we release more from the turbine, we are getting colder water within the reach. And then that would mean that there will be high retention and fishes can go there and fish. I mean, a lot more. Yeah. And so it's basically just a balance between, okay, how do we manage the reservoir while reaping all the benefits of hydropower, recreation, and all those things, and then also creates a very good conducive environment for the fish downstream, right? And so this balance is what we are reporting, or we are um, positing that a tool like um, THORR can afford us or can help us come up with this balance. And for this paper, I think this paper just recently got accepted. We published this work in the in water resources research. I'll share the updated link and paper type. I mean the link to this paper, maybe with Mariel, and she can disseminate that too alongside with the slides. But like we've published this just to demonstrate the possible applications of THORR, right? And just to finish off, I want to just highlight a little bit on the future applications that we are trying to look at within a river network. We know that there are several things that can facilitate or I mean just influence the formation of harmful algae blooms. And I know harmful algae blooms have been heavily researched in I mean coastal regions and all that, but then we do not see a lot of that research in riverine environments. And then I mean, using a tool like THORR, we want to assess how water temperature variations and how we operate the dams. I mean, dams slow down the water and can encourage the growth of harmful algae. And so considering all the nutrients and all that, if you combine that with THORR data, how can we assess water temperature harmful algae blooms in riverine ecosystems, right? And with that, we are using several other tools in addition to THORR to help us do this research. And we are currently trying to expand our territory from the Columbia River Basin. We are adding the Mississippi River, which has experienced a lot of harmful algae bloom, and then we will expand it to other major rivers within the conus or the continuous United States. Yeah. So that's basically some of the future directions or trajectories that we're trying to see and apply for too. And just last summer, we also did a little bit of um, preliminary study just to look into data centers around, which is springing up very much around the Columbia River. They usually like to set up close to rivers, and I'm pretty sure you can all guess the reason why. Because now, if these data centers are springing up, they need water or constant water supply to cool their systems, and we wanted to see how do whether the data centers have any impact on river temperature. this is something that we are interested in also looking at. And it's very interesting if we use THORR to maybe tease out some things. It could be that they are not affecting it in any way, and that would be very pleasant to hear. But then it would be very alarming if they are actually affecting water temperature in any way. Yeah, so that's also another thing that we are interested in looking at. And just to conclude, and yeah, I'm
George,
a little bit,
I
yeah.
may pause us here, and why don't you keep this up while we answer some questions? Because I actually think a few of these questions touch on this nicely, if that's all right.
Yeah, definitely. Yeah. So, yeah, and I think this is a very good slide to conclude on. So that works fine. Yeah, yeah.
Perfect. That sounds good. I welcome folks to turn on cameras, raise your hand, and ask questions. To kick us off, we had just kind of a foundational question around for satellites. When we say observing temperature, like what does that mean for a satellite to be able to observe temperature? For folks who are maybe a little more familiar with something like a thermostat.
Oh, yeah. So yeah, thank you very much for this question, though. So satellites, and I always want to take this from a more relatable perspective, right? If you take your normal camera, you're able to see regular colors that are visible to our eyes. But if you go into advanced military cameras, which I think many people might have seen in the movies, right? They do these thermal infrared cameras where in the night they're able to see people moving with some sort of body heat temperature. So that's what the satellites do. They observe the thermal heat, infrared radiating from the earth, right? And that is what the observation that we take, and then we convert it to water, sorry, to temperature from the earth. And it goes through several corrections for atmospheric corrections and all those things. That is a little another science of its own. But then it's basically observing heat radiating from the earth, just like the same way a camera would um, take a shot of regular colors. These satellites have sensors that can take um, shots of the thermal infrared radiating from the earth. Yeah,
Great. Thank you, George.
yeah.
A nice analogy for that as well.
Hmm.
We also have a question. Early on, you talked about one of the trade-offs being the spatial resolution and the width of rivers when
Hmm.
you're talking with satellites. And so folks
Yeah.
are curious with THORR, what is the smallest river that you could kind of measure with this?
Okay, good. So first of all, with all the input data that we use, it has the smallest. We basically use the Landsat data to help us generate. So Landsat, the thermal infrared band, we can go as far down as 30 meters. So um, to be fair, you say every river that is 30 meters or bigger, we can measure it with the satellite remote sensing. But then with THOR, because we are adding additional data to help us estimate this water temperature, like the kind of terrain around the water and all that, around the river reach, the kind of climate that that particular location is in and all that, the time of the year, we are able to generate even smaller than 30 meters, right? It goes through this information goes through the machine learning or the random forest, and it helps us generate this data. Yeah.
Great. Thank George.
Mhm.
Erica, I see your hand if you want to ask a question.
Super. Oops. I just turned my camera off and then on. Should be okay. There we go. Thanks. Two questions. One is I'll start with the first, which is it looks like Thor matches the temperature time series of individual sensors really well, but I noticed sometimes it was off on the peaks, and because of George, what you described about like temperature stress, it's like if Thor is not quite matching the peak, but let's say the peak is in a range of stress for salmon, is there a way that you could refine how Thor models the peaks? Because that is like the difference between, like being under stress and then mortality. That's my first
Yeah.
question.
Yeah. In terms of like, first of all, a way to refine it, the I would say from a very broader perspective, the best way that we would be able to refine THORR is to get more data, right? Because it's always generated based on data. So one of the approaches that we are going with is that let's say over in the next few years we'll sort of rerun the whole model for THORR, and then because by that time we would have generated new data, like in situ data, and then we use it to sort of refine the estimates. So source data as it is right now is likely going to be updated in a better way. But then one of the advantages which we want to focus more on is long-term trends. And you know that if we look at these long-term trends, then the individual peaks that vary may I would say vanish in the long-term analysis, right? So long-term analysis is one of the things that we want to usually focus on mostly because now we have 40 years of data, and if we're able to use that to assess, just like, well, the random blips or random errors in peaks may occur, but then if you look at it from a long-term perspective, then you will generally be able to capture trends and all that without maybe, yeah, but then if you want to go in detail, then THORR may not be able to afford you that specific detail that you need. For example, I wouldn't recommend THORR as the like sole source of data for a specific study on, like, like something that more like would go to a level of of a lab scale fish study, right? That wouldn't be the best, but then for large scale or long term assessments, then that would be appropriate for it. Yeah.
Okay, interesting. Is it okay if I ask one more question? I don't want to get in front of anybody else.
Go for it, Erica.
Okay. Last question is more for like all of the colleagues on the call, because George, as what you described is like, yes, you can pull water, colder water from the bottom of a reservoir.
Hmm.
But we know that over time, like we've known about this heat stress for a long time, and there's also, issues with low dissolved oxygen in that with that cold water. But the question for the people on the line is like, how come that hasn't been a solution more so, why isn't the use of the bottom of the reservoir water used to mitigate the temperature impacts created by the reservoir? So that's my question. Why
Oh
isn't
yeah.
hasn't it already been a solution? Or is it,
Okay, yeah. So I would want to highlight some places where so what so you know there are certain dams that you can do multi-level discharge, right? You can discharge from midway where the water isn't like way too cold or way too warm. Like you have midway and you can discharge from the very bottom or the top, right? And it is being used in certain areas, right? The Dual Dam, for instance, which is also along, I think, um, yeah, it's in Western Washington. They do multi-level discharge. There are several other dams in Western regions that do that, and in California, for instance, they do all those things. But one thing I would say is the reason why it's not, I mean, popular right now. Imagine a dam which has been constructed like with, I mean, it would be difficult to retrofit these dams. Let me put it that way. It wouldn't be economical to say, I'm going to demolish this whole dam and construct a new one that can do multi-level discharge. So with the old ones that we have, we just have spill or bottom release, right? That's the only thing we can work with. So we just do that sort of balancing game if possible. But then there is that also the need for the primary purpose for which the dam is serving, be it flood control or like hydropower. So it's being done, like Shark and other dams are doing it, right? But then there are it is not very easy to implement it in dams that do not already have those facilities in place, like retrofitting and all those things. Yeah.
Great. Thank you, George. I really appreciate that context. I know we're a couple minutes over. If you've got time, we can take one more question.
Yeah, happy to.
And for those who want to say, I know that last one touched on actually a couple of themes about just the variations of the different dams and where therefore this management strategy may or may not be relevant. So that's great. Jean, if you want to go ahead and ask your question.
Yeah, thank you. Can you hear me?
Yes.
Awesome. Thank you. Jean Buckner here, president of the Friends of the Snoqualmie Valley Trail and River. And we are a not-for-profit organization working in conjunction with the Orca Conservancy, taking river temps on the Snoqualmie River. We have about 40 volunteers, and we go out every Saturday between June and October, every second Saturday between those months at noon, and take temps via manual thermometers as well as these hobo electronic monitors. And what I'm trying to find out is if this type of THORR data could be used to triangulate with our data to see how accurate we're being, if we can get, some kind of confirmation from another real, truly scientific source, that would be great. We take our temps in flowing water, generally about 3 to 4 feet out from the bank. And our river is relatively wide. I don't know, exactly how THORR would take the temperature, and I'm guessing we couldn't expect that the satellite would be above us at noon on the days we need it to be.
Yeah.
So I'm just trying to find out, George, if this might be relevant to us to try to use THORR to triangulate our data, verify our data, make people think we're smarter than we are by getting folks like you to give a look at our project.
All right. So first of all, that's great work, and I have had some experience with hobo loggers. Yeah, I really enjoy working with them sometimes. I mean, but with first of all, THORR, I don't think we have data for the Snoqualmie River right now. Yeah, our current state, we just focus on the Columbia River and its tributaries. And like I said, we are working on expanding it. So hopefully, if we get to include the data on that particular region, then it will be very helpful. Number two, what I want to say is that THORR is sort of open access, and anybody can also adopt THORR and then implement it in their small particular region. And like although I mentioned we developed this whole thing in collaboration with Greatfig, they're currently in the process of setting up THORR for just their systems that they are interested in, right? But in terms of using THORR data to corroborate your hobo data, I feel you may not get exact matchups between satellite overpasses and your hobo logger recordings, but then you could tease out trends. I really like talking about trends, right? Because now, in the absence of exact matchups, you have to work with what you have, right? And if your exact matchups are saying that in the month of or in the when you look at August temperatures within this particular region, the August temperatures have been increasing for the past 5 years. And then you go to THORR, and THORR also says the August temperatures have been increasing for the past 5 years. You may not get exact relationships, but then now we are able to say, well, THORR is saying it's increasing. Our data is also saying it's increasing. So yeah, there could be some truth there, right? So I feel in the absence of exact matchups, trends speak a
Trends.
lot. Yeah.
That makes good sense. Thank you. And we are a salmon river, so please consider putting us on your eventual
Yeah.
future
I'm I'm
list.
I'm happy to extend. Yeah.
And
Thank
George,
you.
maybe something when we follow up with folks, to share, because many on this call are doing monitoring, is what you've seen in terms of spatial temporal resolution for monitoring data being kind of a minimum baseline when you're going to do expansion to other watersheds, so that folks can be thinking about that application and lens now as they're collecting data, and as others expand THORR.
Yeah. Yeah. So with the I like, so with number one, with monitoring or mon monitoring data, it's very important that THORR has, I mean, as much data as we can get, right, to help develop THORR. But the one concept behind THORR is that, and I come from Ghana where we don't have a lot of data, so I think I was a little bit biased when I was focusing on THORR, that I want to develop something that works in the US that you can probably implement the same thing, even if you don't have data in Ghana, right? And I feel so even within Washington or the Pacific Northwest, because we've trained it on available data, even if you don't have data already, you can probably pick the trained THORR model and then maybe apply it in your region. There may be some errors, but then I feel the lack of data may not be the prime limitation. But then the more data that we get, the better, right?
Yeah, I appreciate those reflections, George, for sure. And
Yeah.
definitely that motivation makes a lot of sense, and the beauty of modeling with that. Well, I appreciate you saying on a little extra for these questions. There are a few more in the chat that we can just follow up with folks directly on, but so appreciate everybody's time, thoughtful energy, and monitoring that you all are also doing to complement this. That's a cool to see the broader ecosystem of science around this issue in particular. But with that, thank you all and enjoy the rest of your Tuesday afternoons.
All right. Thank you. Have a good afternoon.